Hi, we are Group 53. In this presentation, we're going to cover our project for SC4000 machine learning. As you know, LLMs are very popular nowadays, with tools like ChatGPT and DeepSeek becoming integral parts of our daily lives. So in this project, we are going to predict human preference between two large language models' responses to a given prompt. So we have response A from model A and response B from model B. Which response would the user prefer? Um, there's three outcomes to this question. Either model A is the winner, model B is the winner, or it's a tie. We evaluate this performance of our implementation using log losses, which means the lower the score, the better. Before we go into the implementation, we would like to discuss our research question in depth. So first is the high dimensional text data. As you know, the prompts and responses are in human natural languages, which are good for human understanding but bad for machine learning and training. Next is the subjective preferences. As you know, the human preference on something is always unpredictable, right? There are so many factors that could affect our daily choices, including subjective factors like our mood. So it's very hard to predict this. Next, we also have an imbalance of our training sets, whereby we have uneven distribution of the different outcomes, A, B, or tie. Also, our training set is not explicitly labeled with what a good response is. So, with our learning, our model is going to learn that what kind of response is going to be preferred by human. And we are also constrained by our computational environments. We have a restricted Kaggle environment whereby we only have two T4 GPUs, and we also gets restricted under the fixed 12 hours execution time. One important thing is that our model, even though trained on the training set, but it also must generalize well on unseen prompts and responses, because as a large language model, we will never be able to predict what the user is going to give the prompt in the next question, right? So this is our approach to this research question, responding to the challenges highlighted in the previous slides. First, we're going to talk about data exploration. Then we're going to talk about how we do pre-processing and parsing. Then we're going to talk about our embeddings, feature engineering, Ensemble model, and lastly, our calibrated predictions. So first is our data processing and augmentation. We begin by concatenating the JSON conversation into a text string. And then we removed the 35 invalid training samples with data cleaning. And lastly, we did one very important thing, which is a swap augmentation. It duplicates each sample by swapping the response A and response B and inverting the winner label. So by doing this, right, we in turn doubles our training data and also reduce our position bias, improving the model's generalization. This is actually a very useful tactic, and will show its results in the later slides. In the semantic and statistical features part, we choose to use MPNet as our feature generator. It is very good at creating these semantic embeddings that converts our natural languages sentences into fixed length dense vectors that represents meanings. So as an output of this MPNet, right, we get very useful features like cosine similarities, L2 distances, text statical features, and interaction features like dot products. These features, in turn, are represented by numeric relationships that machine learning models can learn effectively. So in this implementation, we are using three gradient boosting models, LGB, XGB, and CAT. So we train each class, winner A, winner B, and winner tie, with a five-fold validation. And we then use an Ensemble weight optimizer to find the best blend coefficient of the three models to minimize the log loss. So now we have a basic idea of how our implementation is. We're going to talk about why we use the techniques we choose. So we have many different techniques in this project, and we did not use them for fun or by coincidence. But these are the results of our tireless attempt to push for better performance. In this section, we're going to explain why we did what we did. First is the embeddings. So we actually did comparisons between the different models, and we found that MPNet has the best performance of 0.42% better than the next performing model. So it also gives a very good trade-off between the accuracy and the computational resource it requires. That's why we choose MPNet as our feature generator. Next, why do we choose to ensemble the three gradient boosting model? Why don't we just choose the best one out of them? So again, this is because we did an experiment on this, and our results show that the Ensemble was 0.34% better than the best single performing model, which is Cat Boost. So this Ensemble model utilizes the strength of all three models and also give us a very good diversity that captures more patterns and leads to a more stable and robust final prediction. In experiment 3, we are trying to find out that with the features, so many features we have, do we just use the embedding or do we use the statical features or do we use a combination? So first we compare in the first screenshot. We realize that the statical features actually gives very weak improvement to our results as compared to using embedding only. But then we further explore and we realize that instead of using the base set of 33 statical features, if we switch to use the enhanced set of 49 statical features, which includes features like polynomial transformations and interaction terms, then it is able to give us a better improvement of 0.15%. So in the end, we choose to use a combined model of the embeddings and the enhanced set of statical features. In experiment 4, we compare the cross-validation folds. We compare between 2-fold, 3-fold, and 5-fold. We realize that the 5-fold gives us the best performance with the lowest log loss, but also with acceptable variance. In the last experiment, we demonstrate the tremendous improvement brought about by response swapping. So as I mentioned, not only this brings about the biggest improvement so far of 2.4%, but it also doubles our data, reduce our chance of overfitting, and uh, our fix our problem of position bias, teaching the model to be more symmetry. So as a summary, these are the tactics we use to inch towards a better score and a higher competition ranking. Using a combination of this, our best score so far is 1.01 in the public leadership board, giving us a relative ranking of 64% in the Kaggle competition. Yep, that's all for us. Thank you.